Welcome everybody, my name is Samuel Budd and today I'm going to be talking to you about surface agnostic metrics for cortical volume, segmentation and regression. Irregularities in cortical folding and microstructure development have been implicated in a range of neurological and psychiatric disorders, including autism, Down syndrome, epilepsy and psychosis. The cerebral cortex is a thin layer of grey matter tissue at the outer layer of the brain, and studying it is important for improving understanding of cognitive and neurological disorders. There is a strong need to model cortical development in at-risk neonatal populations. However, due to the heterogeneous and highly convoluted shape of the cortex, it has proved highly challenging to compare across populations. Currently, most studies of the cortex use surface mesh models, which fit mesh models to inner and outer cortical boundaries, following pipelines which perform tissue segmentation, followed by surface tessellation with intensity-based refinement. Summary measures of cortical thickness and curvature may then be estimated from the Euclidean distance between mesh surfaces and principal curvatures of the white matter surface, respectively. For developmental cohorts, the fitting of surface mesh models is even more challenging due to the relatively low resolution and likely motion corruption of these datasets. This leads to artifacts and partial volume effects or blurring across tissue boundaries. Methods to tackle these problems individually exist, but they are highly tuned to high resolution, low motion research datasets and do not always transfer well to clinical populations. As an alternative, several groups have proposed techniques for extracting cortical surface metrics from volume data directly. However, volumetric fitting approaches such as these have not yet been validated on developmental data, and their slow run times limit their utility for clinical applications. In this work, we seek to develop a novel application for cortical metric prediction from clinical developmental data through deep learning. We propose the first probabilistic deep learning tool for cortical segmentation and metric learning, and validate the method against cortical thickness and curvature prediction for data from the Developing Human Connectome project. The tool is used to predict cortical metrics for a Down syndrome cohort in which surface-based analysis often fails, and our probabilistic approach returns confidence maps which can inform clinical researchers of areas of the brain where measurements are less reliable. Our proposed network architecture augments the popular UNet architecture into a 3D multitask prediction network. We introduce a branch of fully connected layers prior to the final convolution of the UNet, as shown on the right. The network predicts a cortical segmentation through the standard UNet architecture while simultaneously regressing a cortical metric value for every voxel in the image. These two tasks are strongly coupled, and as such we design the network regression branch of our network to see a large amount of information from the segmentation path. We use a cross-entropy function, loss function for the segmentation task, and consider two different loss functions for the regression task, mean squared error and the Huber/L1 loss. The latter is considered to encourage smoothness of regression predictions across neighbouring pixels by being robust to outliers, and a property that should hold for cortical metric predictions. We propose a probabilistic extension of our network in which we introduce drop block to our network during training and test time, and this approach ensures variation in our network predictions during inference, and this forms the baseline of our probabilistic experiments. We propose an alternative probabilistic segmentation and regression architecture based on the PhiSeg network to model prediction variation across multiple scales and generate multiple plausible predictions for each input. We extend the PhiSeg architecture with the fully connected layers in the same way as we extended our UNet model to regress cortical metric predictions for each voxel. From these, we generate confidence maps for each prediction by sampling multiple times for each probabilistic network. This results in a range of segmentations and a range of metric predictions for each voxel, and we argue that the larger the range of values predicted for a given voxel, the less confident our network has been in predicting a value for that voxel. Data for this study comes from the Human Developing Connectome project. The study contains 505 subjects aged between 26 and 45 weeks. Tissue segmentations and surface metrics for training are derived from the DHCP surface extraction pipeline. The second clinical Down syndrome cohort of 26 subjects was collected with a variety of scanning parameters aged between 32 and 45 weeks. We project surface-based representations of cortical biometrics into a volumetric representation using a Rubin constrained method provided by the HCP project pipeline. This operation is performed for both hemispheres of the brain and then combined into a single volume where overlapping metric values are averaged. These volumes, together with the tissue segmentations, represent the training targets for the learning algorithm. 400 subjects used for training, 50 for validation and 55 for testing. And during training we sample class balance 64 by 64 by 64 voxel patches from each subject's volume pair, and we test on the entire volume of an image using a 3D sliding window approach. We conduct our experiments to predict two different cortical metrics, thickness and curvature. So, we establish a baseline for the simultaneous estimation of cortical segmentation and metric regression. We find minimal differences in performance using the Huber loss function instead of the MSE loss function on the regression task. On the right, we show example outputs produced by our best performing model in comparison to the ground truth. We can see that our network successfully extracts accurate cortical metric predictions directly from the input MRI, maintaining the structural variation we expect to see across the cortex. We notice that some extreme values have not been accurately predicted, such as in the cortical regions at the bridge between the two brain hemispheres for curvature prediction. However, the extreme values that are present in the ground truth data are an artifact of the surface-based metric prediction method. Hence, it is less important to replicate these as precisely. We consider probabilistic extensions of our previous best performing method and report the performance measures for probabilistic experiments on the right. We find that introducing drop block layers into our network has improved segmentation accuracy, but metric accuracy has declined. PhiSeg has not improved either segmentation or metric estimation performance, but in these experiments PhiSeg training was often unstable and took too long to converge than other methods. While our error has increased, the ability to generate confidence maps for these predictions increases their value, and show examples of these confidence maps projected back onto the brain surface on the right. We assess the performance of our method on a challenging Down syndrome MRI dataset for which the DHCP pipeline fails to extract metrics correctly for many subjects. Since the ground truth for this dataset is error-prone, we demonstrate the performance of our method qualitatively and through population comparisons to the healthy DHCP test set used in previous experiments. Our method produces more reasonable estimates of cortical thickness than the DHCP pipeline, thus showing evidence of our method's robustness to challenging datasets. Population statistics indicate that our method produces metric values in a sensible range for cortical thickness, and this is shown on the right. However, our predicted distribution for cortical curvature is not consistent with healthy patients, indicating that curvature and other more complex metrics remain challenging. Looking forward, we've proposed an automatic, pathology-robust method to predict cortical metric values from any T2 weighted image. Our method is fast, robust, and precise. We've experimented with multitask variants of the well-known UNet architecture to demonstrate how readily applicable deep learning is to predict cortical metric values in a reproducible way. The biggest advantage of our method is that we can produce cortical measurements for pathological cases. However, the curvature example shown on the previous slide shows that more complex metrics do remain challenging, and that we will need to further verify the robustness of our method in a clinical setting. A natural extension of our method is to automatically extract surface meshes from unseen data to enable proper visualization of our predictions. And our approach naturally extends to predicting sulcal depth or myelination. In conclusion, we offer an open source framework for the extraction of cortical biometrics directly from T2 MRI images. This is the first of its kind that shows potential to be independent of age, image quality, or presence of pathologies, and likely extendable to any cortical property. We have tested our approach on a challenging pathological dataset for which we have not been able to reliably extract metrics with conventional methods like the DHCP processing pipeline. We expect that our future work will open new avenues to the analysis of cortical properties related to human brain development and disease in heterogeneous populations. And with that, we'd like to thank you for listening and invite you to join our discussions over a poster. Thank you.